Hello, hello. My name is GRV.SRIRAM. I am from Department of CSC Data Science. My roll number is 47 and my AIT subject is Triple Elements of Electrical and Electronics Engineering, and my topic is Capacitor Overview. Capacitor Overview. Understanding the capacitors in electronics. First, let me say you about the introduction of this topic, Capacitor Overview. And this presentation explores the fundamentals of capacitors, focusing on their definitions, functions, types. We discuss key concepts that are essential for understanding their role in electronics and especially in the context of circuit behavior. Number one, the capacitor basics. Definition and function of capacitors. Capacitors are electrical components that store and release electrical energy in a circuit. They consist of two conductive plates separated by an insulating material called a dielectric. When voltage is applied, an electric field forms, allowing the capacitor to store energy. Capacitors are essential in numerous applications, such as smoothing out signals in power supplies and timing applications in circuits. Types of capacitors. There are several types of capacitors, each with different characteristics suited for various applications. Common types include ceramic capacitors, electrolytic capacitors, tantalum capacitors, and film capacitors. And ceramic capacitors are often used in high frequency applications due to their stability, while electrolytic capacitors are ideal for power supply circuits due to their high capacitance values. Tantalum capacitors are used in compact devices for their reliability, and film capacitors are noted for their low inductance and excellent characteristics. And next one, the capacitance measurement. Capacitance is measured in farads, F, with smaller capacitors often expressed in microfarads, μF, or picofarads, PF. To measure capacitance, a capacitance meter can be used, which applies a voltage to the capacitor and measures the charge stored. Now, the formula for capacitance C is equal to Q by V, where Q is the charge stored and V is the voltage across the capacitor. Accurate measurement is essential for proper functioning in electrical circuits. And second topic is the two capacitor problem. Circuit configuration. In the two capacitor problem, capacitors can arrange in series or parallel, affecting their overall capacitance in series, the total capacitance C total is given by 1 by C total is equal to 1 by C1 plus 1 by C2, leading to a smaller equivalent capacitance in parallel, and in the parallel the total capacitance is simply C total is equal to C1 plus C2, resulting in a larger equivalent capacitance. The arrangement significantly influences how charge and voltage are distributed across the capacitors. Charge and voltage relationships. The charge Q on capacitors in series is the same, but the voltage V across and each capacitor can differ, and it is related to their capacitance values. Conversely, in parallel, each capacitor experiences the same voltage, but the charge stored varies according to each capacitor's capacitance. This relationship is crucial for analyzing how energy is distributed in circuits with multiple capacitors and directly impacts circuit behavior such as discharge rates and RC time constants. Energy storage comparison. The energy E stored in capacitor is given by E is equal to half into C into V square. In two capacitor system, the configuration affects energy storage. In series, the effective capacitance hence energy stored is lower compared to parallel configuration. Understanding the energy distribution allows for the better design choices in circuits, particularly in applications requiring specific energy storage capabilities or discharge characteristics. And at last, the conclusions. In conclusion, understanding capacitors and their behaviors in different configurations is essential for effective circuit design. The two capacitor problems illustrates the fundamental principles of capacitance, charge distribution, and energy storage. Mastery of these concepts provides a foundation for advanced topics in electronics and aids in troubleshooting and optimizing performance in electronic systems. And in final conclusion, capacitors are fundamental components in electronic circuits, widely used for energy storage, filtering, signal coupling, and timing applications. And they have, and here are some key conclusions for from an overview of capacitors. They have energy storage. Capacitors store electrical energy in an electric field, releasing it when needed. This makes them essential in power supply circuits for smooth voltage fluctuations. Next one, types of capacitors. There are various types of capacitors, including ceramic, electrolytic, tantalum, film, and supercapacitors, each with unique characteristics suited for specific applications. Capacitance. The capacitance of a capacitor is measured in farads F. Determine how much charge it can store. Factors influencing the capacitors capacitance include the surface area of plates, the distance between them, and dielectric material used. Dielectric material The dielectric material between the plates significantly affects the capacitor's performance, including its capacitance, voltage rating, and temperature stability. Applications. Capacitors are used in wide range of applications from decoupling and noise filtering in electronic devices to energy storing in power systems and timing circuits in oscillators. Charging and discharging. Capacitors charge and discharge quickly, making them ideal for applications requiring rapid energy delivery, such as in camera, flashes, and defibrillators, impedance, and frequency response. Capacitors exhibit varying impedance depending on the frequency of the applied voltage, which is crucial in AC circuits and filtering applications. Polarity. Some capacitors, like electrolytic and tantalum types, are polarized and must be connected with correct polarity to avoid damage. Lifetime and reliability. The lifespan of a capacitor can be affected by factors such as temperature, voltage stress, and electrolyte drying in electrolytic capacitors. Proper selection and uses are essential for reliability. Advancements. Ongoing research and development are leading to capacitors with high energy densities, better for performance, and smaller sizes, catering to the demands of modern electronics and renewable energy systems. In summary, capacitors are versatile and indispensable components in electronics, with their properties and types tailored to meet the diverse needs of various applications. Understanding their characteristics and proper usage is crucial for effective circuit design and functionality. And this is the overall conclusion of the topic capacitors overview. Thank you.